Smith from IBM Research on communication in a quantum context. What would Shannon do? Dr. Graeme Smith obtained his bachelor's degree from University of Toronto in 2001, his master's from Caltech in 2004, and his PhD again from Caltech in 2006. He is presently a researcher at the IBM Thomas J. Watson Research Center in the Physics of Information Group, which includes Dr. Charles Bennett, who was at DEI for CONSAS 2008. His research interests are computation and communication in noisy settings, coding theory, quantum Shannon theory, geometry and packing, cryptography, quantum estimation and detection, and quantum devices. Please welcome.
Overview today of the theory of communications and information in settings where quantum effects are important. Okay, so the study of information and communication goes back a long way, but the person that really started the modern study of information theory was Shannon in 1948. Okay, and I was just talking to some students at lunch, and I guess second year in electrical engineering and computer science, you study information theory. Okay, so it's pretty basic. So the sort of this quote from Shannon's original paper, I think, does a nice job of summarizing the kinds of questions that we usually think of as information theory. So it's broad enough to include source coding or data compression, channel coding or error correction that I want to talk about a lot today. Okay, channel coding or error correction that I'm going to talk a lot about today, signal detection, cryptography, etc. Okay, and really one of the central questions in the theory of information is trying to communicate reliably in the presence of noise. So the way we model this is we imagine you have some noisy communication channel, I'll call it N. It has some input signal X and some output signal Y. And the relationship between the input and the output is that the probability of getting some output Y, given that you chose input X, is given by some conditional probability distribution. Okay, if I give you a single use of a channel like this and it's noisy, there's really very little you can do. You're not going to be able to communicate reliably. But really one of the, the beautiful thing that Shannon realized was that if you have many independent uses of a noisy channel like this, 1, 2, all the way up to N, if you use them in parallel, it's possible for a sender to encode some intended message M into all the inputs of these channels in such a way that a receiver who gets all the outputs can do some decoding operation to get a fairly good estimate of what the input was. So the point is that as the number of channel uses gets high, you can, with high probability, let this M naught, with high probability, this M naught will be equal to M. Okay. And the way you should think of this is maybe these are different pieces of a memory that you're using, or these are uses of an optical fiber at different times. The point is, as long as the noise is sort of independent in these different uses, you're going to be able to send information reliably. And in fact, we'd like to be able to send it at very high rates, right? So what we'd like to know is what's the maximum rate at which you can transmit information with errors vanishing as the number of channel uses grows. Okay? So a priori, this is a complicated question, right? It involves optimizations over asymptotically large strategies that you might use for communication. But really one of the most beautiful results in information theory is the fact that it's possible to characterize the capacity of a noisy channel like this in terms of a simple formula, a simple optimization over a single use of the channel. Okay? The capacity of the channel is just given by the maximum amount of correlation you can generate between input and output of the channel, where the correlation is measured by this mutual information quantity. The mutual information, I'll discuss more in a while, but it's basically just the difference between the sum of the individual entropies of these variables and the joint entropy. And an important consequence of this simple formula is that the capacity of a noisy channel is additive, in the sense that if I take two channels, like a wire here and an optical fiber here, the capacity of the joint channel, when I use them together, is exactly equal to the sum of the individual capacities. Okay, so this is actually, I think it's a very beautiful theory, and it's very useful in engineering practice. But it does have at least one problem, right? And that's the topic of our discussion today, or of this whole conference. The world isn't made of random variables like that theory I discussed. It's made of atoms and photons, and these things obey quantum mechanics. And we'd like to develop a theory of information that's rich enough to include quantum effects too. Okay? And this isn't news to anybody, right? So even back in, so everybody knew, Shannon even knew that ultimately you were going to have to take into account quantum effects in your systems if you were going to get accurate descriptions of them. So this is a quote from a review by John Pierce in IEEE Information Theory Transactions called The Early Days of Information Theory. And, maybe I'll read it. He says, "I think I've never met a physicist who understood information theory. I wish that the physicists would stop talking about reformulating information theory, and they'd give us a general expression for the capacity of a channel with quantum effects taken into account, rather than a number of special cases." And you can see from what he's saying here is that he's basically seeing these quantum effects as an annoying source of noise in your system. So the quantum effects are telling you that, well, I can't measure things as precisely as I'd like to, or I can't localize things in the way I'd like to. And it's sort of a, I guess, it's a very negative view. But, and it turns out, in fact, more than just being some source of noise in your system, it's possible when you actually reformulate information theory a little bit to use these quantum effects to your advantage. Okay? So it turns out the right way to think of information theory in the quantum setting is to go back to this original definition, if you like, of Shannon of information theory and expand what you mean by messages. So Shannon was thinking of messages as being these random variables that you're trying to transmit. And he made a lot of progress with that. But it turns out you can do a lot more if you start thinking about not only transmitting classical messages, but also expanding your notion of a message to include the transmission of the quantum state. Okay? And once you do that, in fact, it leads you to all sorts of useful protocols. Okay, so for example, by thinking of quantum effects as a resource, or by thinking of your signal states as being made up of quantum states rather than classical, you immediately get to this idea of quantum cryptography, which allows you to transmit classical information with a level of security that's not possible with purely classical theory, by taking advantage of your ability to transmit quantum states. And similarly, if you imagine having a computer that can exist in superpositions of different states rather than has to pick a definite state, it's possible to develop algorithms for that kind of computer, a quantum computer, that can do very difficult problems. They can factor efficiently, simulate quantum systems very well. And in general, when you start thinking about using signal states that are fundamentally quantum, you get advantages in all sorts of areas, like precision measurement, communications, and cryptography. Okay, and the key idea in all of this is to replace this notion of a bit, which can take on one of two definite values, a 0 or a 1, with a quantum bit or a qubit, which can take on any definite superposition of, say, 0 and 1. Okay? And the key feature of these qubits, or one of the key features, is that it's not possible to measure a qubit without disturbing it. So that's a very important aspect of quantum systems if you're interested in doing quantum cryptography. And in a very related way, it's not possible to clone a system or to make a copy of it. So if I give you an unknown quantum state, there's no way for you to do some physical operation on it that gives you two copies of that unknown state. Okay, it's not a physical, basically because it's not linear. Okay, and in general, qubits are a really useful abstraction for thinking about designing protocols that involve fundamentally quantum effects, like algorithms for quantum computers, cryptography systems, etc. And it turns out then that the right way to think of information is actually in terms of quantum systems and qubits. And it's only in this very special degenerate case that we get this picture of Shannon that we now call classical information. Okay, this should have you worried, right? It's not possible to make a copy of a quantum state. Because it means it's not possible, well, you might have thought that it wasn't possible to do error correction, because the way we think about doing error correction is by introducing redundancy into our coding. Okay? So the fact that you can't actually make copies, or it seems you can't do redundant coding for quantum systems, is actually a big problem. But it turns out, again, this is I think, a priori not obvious, but it turns out it is possible to encode quantum information in a way that's resistant to noise. All right? In exactly the same way that Shannon showed us to encode information, classical information, in a way that's resistant to noise. And again, this depends on having access to, well, if I give you a single noisy communication channel, now it's quantum, it's not going to be possible to transmit with low probability of error. But if you have access to a large number of independent uses, it turns out that you can design protocols or quantum error correcting codes so that if you have some qubits over here on the left, you can do an encoding into all the inputs of the noisy channel that you've got in such a way that a receiver who gets access to all the outputs of the noisy channel can do some decoding on it and get out the original qubits sent. Okay. Now, I really want to emphasize, because it's not possible to make a copy of a quantum state, once you put these qubits in here and act on them in that with that encoding operation, you no longer hold on to the qubits. You've given them up to encode them into a particular signal state. So that's the reason that you can actually transmit quantum information in error-correcting codes without violating this no cloning principle. Because by sending the information, you really give up any interest that you have in it. Okay, so of course we want to do really well. We want to transmit as much quantum information as we can. So as many qubits. The quantum capacity of a noisy quantum channel is just defined as the maximum number of quantum bits that you can transmit per channel use, with errors vanishing as the number of channel uses grow. Okay. Okay, and what I wanted, one of the sort of interesting effects that I want to discuss today relates to this picture. I'm really interested in very noisy quantum channels. So quantum channels that are so noisy that this quantum capacity is strictly zero. So it's not possible to transmit any quantum information with them at all. So as a point of reference, I want to describe the classical channels that have zero capacity. And well, here's an example. I cut the wire, and there's no correlation between the messages sent and received. Just, I want to do a quick poll. Which is the sender? Who thinks the computer is the sender? Who thinks it's the receiver? Nobody. Okay. Well, it turns out, well, there's no correct answer, right? I'm just curious. I think of it as being the sender. Okay, so the set of quantum channels that have zero quantum capacity, or zero classical capacity, are exactly the ones that have no correlation between the input and the output. Okay, so that's a very simple set of channels. But it turns out, because quantum data is so delicate, it requires less noise. It takes less noise to make your channel completely useless than you need to add to make it useless for transmitting classical information. All right, so there are channels that allow some correlations that nevertheless are too noisy to allow you to transmit quantum data. Okay? And it turns out there's a lot of structure to these channels, and it turns out they can do something very interesting, which is very different from what happens in the classical setting. You can find pairs of channels, neither one of which has any quantum capacity. So I have channel N1 and N2. So the quantum capacity of this channel N1 is 0. So I have some qubits here. I try to encode them into many uses of the channel. I do some decoding operation, and what comes out is basically noise. Well, it's not complete noise, but it's not sufficiently correlated with this to allow you to transmit noiseless quantum information, right? So you might have classical correlation, but no quantum correlation. Right? And similarly with this channel N2. So I try to do some encoding. I send my information through the channel, and what comes out is no matter what decoding I use, is not a high fidelity qubit. Okay, and the surprising thing about this is that when you take these two channels together, it turns out that there exist joint encoders and decoders that allow you to transmit large amounts of quantum data with large numbers of qubits with vanishing probability of error. Okay, so what I want to discuss a little bit for the rest of the talk is just how this effect works and what it means for the theory of quantum communication and information. Okay, so here's an outline. Yep, good. For the rest of the talk, first I want to remind you a little bit about quantum states and channels, and then I want to talk about two different capacities of a quantum channel. The first I've already discussed with you, the quantum capacity of a quantum channel, and the second is the private capacity, and that's the capacity for transmitting classical information in a way that maintains security of that information. So in a way that prevents any eavesdropper from learning about it. So this is closely related to quantum cryptography. Then I want to discuss with you a couple of different kinds of quantum channels that have zero quantum capacity, one of them in detail. And then I'll show you how to take two of those channels. There are going to be two classes of zero quantum capacity channels that I described. And I want to show you how to take two of those channels and put them together to get positive joint capacity. Okay, so this is well, the word superactivation is used to describe that. So the idea is somehow the two channels have some sorts of complementary potentials, and one channel activates the potential of the other. Okay, this is back to basics. Let's first describe a pure quantum state. So this is the minimum uncertainty quantum state. And let me describe the simplest possible quantum system that's non-trivial, a two-level quantum system, so a qubit. So the state of a qubit is described by some superposition of, so this should be a ket, so should that in there. Some superposition of two different states, 0 and 1. These are orthogonal states. And the way I completely characterize the state with the amplitudes of 0 and 1. Now, the state has to be normalized, so the mod squared of the amplitudes, their sum is equal to 1. Okay? And you should just think of this as a vector, a complex two-dimensional vector. And the rules of the game are like this. You get to pick a basis, and once you picked that basis, you can measure in that basis. And the probability of getting the outcome associated with the zero vector is just the inner product of the state of your system with the zero vector modulus squared. Okay? So in this case, I could measure in the 0, 1 basis, and probably I'll get a 0, but perhaps I'll get a 1. Right? And really, the essential thing that makes this theory quantum rather than classical is that you don't have to pick this 0, 1 basis. If you restricted your attention always to this single basis, you'd have basically classical probability theory. Okay? But in fact, you can choose any other basis you like. So for example, I could choose this plus-minus basis, where plus-minus is just 0 plus or minus 1, properly normalized. And I could measure in that basis instead. So now probably I get a plus, perhaps I get a minus. Okay? And you can, I guess, generalize pretty simply to the D-level system. You just let this vector be a D-dimensional complex vector rather than 2. Okay, so that's the simplest quantum state, but in general, a quantum state might be mixed. As I said, pure states these are the minimum uncertainty states in quantum mechanics, but you can also have a mixed state, which is where, well, with some probability p sub I, you have state psi sub I, and this is kind of important, so I want to write it over here. Sorry, my PowerPoint is not working that well. So the idea is, if I have some quantum system that has probability p sub I of being in state psi sub I can describe that with the density matrix that's just given by this mixture of the projectors onto the associated vector. Okay. All right, and one nice thing about these mixed quantum states is that you can think of them as being part of a bipartite, so a two-level, or a two-system, joint system, that's in a pure state. Okay? So, and the idea is you can imagine that this rho is just given by some projector onto a pure state, psi, on some larger system, AB, if this lives on B, then an equivalent way to write this mixture is just as the partial trace of some larger pure state. Right? So this is already kind of weird, right? Because it's possible that I can have two systems that are in a pure state, so they're in a very definite state, but when I look at just one of the subsystems, in fact, it's a very mixed state, or it's completely unknown. So this is a reflection of entanglement again, and the idea is, you can have this pure part that has a pure whole that has mixed parts, and that's definitely not something that happens in classical theory. Okay, I'm going back to the whiteboard. Sorry. So now I want to discuss how do we think about how mixed a quantum state is. So any quantum state, remember, can be thought of as a pure state followed by a partial trace. And the way we measure how mixed this mixed state rho is that we look at the von Neumann entropy. So the von Neumann entropy of rho is just given by minus trace of rho log rho. And in some sense, this measures how much information, there is in this quantum state. And in a very specific way. If I'm given n copies of this rho sub b, and it has some purification to some psi sub a, it's possible for me to reversibly compress all of those independent B systems into a space of size 2 to the n times the von Neumann entropy of the state, in such a way that if I hand over that encoded state to somebody, they can do a decoding and recover all of the original entanglement with this A system. And in fact, even better, it's not possible, well, even more, it's not possible to compress it any further. So this tells me, this S of rho sub B tells me exactly how much information is contained in the state. And that's the way that space that I compress this state into is called the typical space of the state. And it's very closely related to a topic an idea from classical information called typical sets of classical bit strings. The states of quantum theory, and I've talked a little bit about how we measure the information in a state, but now I want to talk about the dynamics of the theory, okay? So I want to talk about noisy communication channels. So, well, here's a simple example of a communication channel. The simplest is noiseless evolution. And this is just given by conjugation of rho by a unitary. So U goes to U rho U dagger. Okay? Where this U is a unitary. But more generally, you could have some noisy evolution. And in fact, the most general kind of noisy evolution is given by the unitary interaction with some inaccessible environment. So any quantum evolution you can describe as mapping state rho. Well, first adding on a system called an environment in some fixed pure state, doing some unitary interaction with that environment, and then throwing the environment away. Okay? So this is the most general form of a noisy quantum evolution. All right? And this is really sort of the beast that we're going to be interested in analyzing. So given a particular unitary, we'd now like to know how much quantum information can I transmit with that. Oh, wait, I don't know. Try to make. Okay, so that covers I guess, some background. now I want to discuss some information theory a little bit. Remember, the quantum capacity of a quantum channel is just the maximum rate at which I can take qubits over here, encode them into some noisy channel, and decode them to recover the original state on the right. Okay? And of course, we'd like to maximize the amount of information we transmit. So what we do, so what we'd like to do is optimize over these encoding and decoding operations. And I should emphasize that these encoding and decoding operations are quantum operations. So if you have some qubits, you want to encode them again into some quantum systems. This is basically a quantum computer. Okay, and really what we'd like to do is understand, as a function of this n, or as a function of this unitary that has all the information about n, what is the maximum rate at which we can transmit information. Okay, it turns out that well, we can't get this nice simple formula like we had for the classical capacity. But there is some quantity that's a little bit like the mutual information that we can use to get some idea about what quantum capacities are. Okay, so it's called the coherent information. It's given by Q1. It's just the maximum over all possible mixed input states here. Okay, so I'm optimizing over some mixed state, I'll call it phi, of the difference between the entropy of the output of the channel, entropy of B, and the entropy of the environment. Okay? Now this should be, the quantum capacity is at least as big as this coherent information. So this should be bigger than or equal to. And the way that you show that is by a random coding argument, just like in Shannon's case. What that tells you is that good quantum error correcting codes exist. They have positive rate even. So the number of qubits you can send per channel use approaches some constant as the number of channel uses grows. And it turns out that, in fact, the quantum capacity is not given by this coherent information, but it's given by a much more complicated formula called the regularization of the coherent information. It's given by the maximum, well, sorry. Since I've defined the coherent information, quantum capacity is given by just the limit over many channel uses, as the number of channel uses goes to infinity, of the total amount of coherent information you can generate with n uses of the channel. Okay? So this is a little unfortunate because this gives us an asymptotic expression for this quantity that we're interested in, and it's not something that we can evaluate in general. Okay? And it turns out, in fact, the quantum capacity can be strictly larger than this coherent information, which tells us that random coding techniques are not optimal for transmitting quantum information. Okay, so this coherent information is kind of it's a little bit difficult to understand, so I want to say a few words about it. First of all, it's somehow related to this no cloning idea. Because, you know, if you wanted to transmit some quantum information, if you wanted to transmit some quantum information from one place to another, it's extremely important because it's not possible to transmit it coherently, say, to two places. It's extremely important that if you transmit from, say, site A to site B, that any place besides B doesn't learn anything about that information, right? So in other words, because of this no cloning principle, if I want to send you information, your friends better not find out about it, okay? And this no cloning basically tells you that this operation, which is, I guess, manifestly not linear, is not linear, right? And the only operations that we can do physically are linear ones. Okay? And somehow this coherent information down here tells us something about how much more information the output of the channel has than the environment of the channel has. And that's why it tells us something about how much quantum information we can transmit, because it's essential that quantum information not be leaked to the environment if it's going to be transmitted with high fidelity. Okay, so this is something like how much secret information we can send to Bob. It's how much secret information we can send coherently, actually. Okay, there's another capacity of a quantum channel that's also very interesting, called the private capacity. And the private capacity, it's very closely related. We have a slightly different setting. Now we want to transmit classical information, okay, from our sender to our receiver. But we'd like to do it in such a way that that an adversary that has access to all of the environments of this channel, okay, remember we think of our channel as being a unitary interaction with some inaccessible environment. We'd like to make sure that an adversary who has access to all of those environments can't learn anything about the messages sent. Okay. This should be phi sub x. I'm very sorry about the problems with this. I should have checked before. Okay. And the maximum rate at which you can transmit classical information privately is given by something called or related to something called the private information. The private information is just the maximum over all input ensembles, right? So I have some random variable x, I have some phi sub x that depends on that, here, it's up here, and I put this phi sub x into the channel. The private information is just the maximum difference between the mutual information between this x and the output of the channel, and this x and the environment. So this is more literally how much more information does the output of the channel get about this random variable than the input of the channel did. Okay. And it turns out, again, that this private information is a lower bound for the optimal rate at which we can transmit privately. So this should be bigger than or equal to. So P of n is just at least as big as this private information. And in fact, you can do a similar trick. You just have to evaluate this P1 of n on n uses of the channel and normalize by the total number of uses, and that gives you the private capacity. And it turns out that this regularization procedure is necessary. Okay, so this private capacity is not equal to this single letter private information. And I should point out, because of this, because transmitting quantum information, if you transmit quantum information with high fidelity, it's necessarily private. The private capacity is at least as big as the quantum capacity. Okay, and in fact, sometimes it can be strictly bigger, which is kind of an interesting case. All right, that covers some definitions. Now I want to discuss a few channels that are noisy. Okay, some channels that have zero capacity for transmitting quantum information. So this one is, I think, it's a very simple example. It should be easy to understand. Imagine I had a quantum channel. I can describe it with some unitary interaction with some inaccessible environment again. So I have some input state psi, and this unitary maps to some output b, and the action of the channel I get by tracing out this e. But what if I looked at the unitary, and before tracing out e, I noticed that the unitary was symmetric? Okay? All right, so if I swap b and e, I get the same thing back again. So a good example to think of is the 50% erasure channel. So I put in psi, and that gets mapped to an equal superposition of psi on the input, or psi on b, and some orthogonal state e on the environment system, and e on b, and some e on b, and psi on e in the other case. Okay? And the reason we call this the 50% erasure channel is that its action is that if I put some mixed state rho into the channel, the output is just a 50-50 mixture of rho and some orthogonal flag. Okay, so if you're the receiver, what you get is half the time you get the original state, and the other half the time you get a message that says, I'm sorry, your state was erased. Okay, and this is sort of manifestly symmetric, so it's certainly an example of one of these symmetric channels. Okay, so I claim that any symmetric channel has zero quantum capacity. Why? Well, suppose that our channel had, this is symmetric, and it had positive quantum capacity. Well, the first thing I should tell you is that this quantum capacity involves many uses of the channel. So I should take many copies of this unitary U acting on some state, and the output is many copies of the output space of the channel and many copies of the environment. But I'm allowed to do some encoding, right? So what happens is, if the channel had capacity, I could take some state psi, do an encoding, put it into many uses of the channel, and out of the channel comes the output. I can do a decoding and get the original state back. Okay? Now the problem with that is that this unitary here is symmetric, and in fact, n copies of it is still symmetric. So if there was some decoding that works on the output of the channel, there would be another decoding that works on the environment of the channel. So I could decode on that too, in which case this entire operation, the encoder concatenated with many uses of the channel and these two decoders would take some input state psi and map it to two copies of that output state, right? It's this operation here. And that's not possible, right? That's not actually a physical operation. And again, the way to see it is that this is not a linear operation, even though any encoder, any channel, and any decoder need to be linear. More specifically, they need to be completely positive trace-preserving maps. Okay? Oops. All right, that's not possible. So as a result, any symmetric channel has got to have zero quantum capacity, and specifically this 50% erasure channel has zero quantum capacity. And that's going to be one of the two channels that I show you how to put together to get positive joint capacity. I'm going to ask you to ignore this, and I'll tell you about something called partial transpose. The partial transpose is a linear operation on a bipartite space. So I have some basis of a space, ij tensor KL, ij on A, KL on B, and the way the partial transpose works, I'll call it gamma of B, is that, well, it just does transpose on half of the, on the B system, but not on the A. So it maps this basis vector to this one. And the way to think about this is if I wrote down a density matrix, rho AB, it has some block form associated with with this bipartite system, and I do transposes within each of the blocks, but I don't move the blocks around. Okay? That's what partial transpose is. And it's possible to show that if some quantum state, rho AB, has partial transpose, so I do this operation, that's not positive, so I diagonalize it, I find that it has a negative eigenvalue, then the state is entangled, okay? But it turns out that if the state has positive partial transpose, so I do rho AB, gamma of B, and that's bigger than or equal to 0, so all the eigenvalues are positive, it may or may not be entangled, but at the very least, it's extremely noisy. And in fact, it's so noisy that it's not possible to use such a state to get any, basically, if I give a pair of people a state, they can't do any local operations that allows them to distill any pure entanglement from them. Okay? And a PPT channel, or a positive partial transpose channel, is just one that enforces this PPT property between its output and the purification. So it's a channel that only lets you make these PPT states. Okay? And it's important to note that this implies that the quantum capacity of the channel is 0, because if you could make entanglement, pure state entanglement with the channel, it couldn't be PPT. But in fact, there exist PPT channels that have positive private classical capacity. Okay, so now I just want to discuss a little bit, what are the conditions for having a private capacity? Well, a channel with private capacity has to allow you to make something called a private quantum state. So a private quantum state is a four-partite state that looks like this. It has a system that we call, a pair of systems called the shield, and they start off in a maximally entangled state that looks like that. So it's just 0, 0 plus 1, 1. And the shield can start off in basically any state. And a private quantum state looks like this, but we allow there to be interactions between this key system and the shield in such a way that we ensure that the correlations between A and B in a particular basis are maintained, but somehow phase information about the correlations gets leaked to the shield system. Now the important thing is that the shield system knows everything about the phase information encoded in AB, so that if I took this mixed quantum state and purified it to some larger pure state and looked at what the environment is holding on to, the AB system is in fact conditionally independent of the E system, meaning that there's this sort of Markov chain structure. So A prime, or this shield system, this should say A prime and B prime. This A prime B prime system knows all of the correlation that E has with the key system, in fact, is mediated by this shield system. It completely characterizes the channel. Okay? And the way that I make this channel is by taking a private quantum state that looks like this and just adding a little bit of noise to this key system, okay, until the whole thing has a positive partial transpose. And that makes sure that I have a zero quantum capacity. But because this looks so much like a private state and there's just a little bit of noise added, in fact, it has positive private capacity. Okay? So this picture I could write down a noisy quantum channel for you that can't transmit any quantum information. However, if you use it, you can transmit classical information privately. So for example, it would be useful for you if you're trying to do quantum cryptography. Okay, now I want to show you how to combine in the last few minutes a 50% erasure channel, which is symmetric and as a result has zero quantum capacity, with one of these positive partial transpose channels that has non-zero private capacity. Okay, and here's the theorem. If I let me write this down. The idea is this: if I have some quantum channel, any channel n, if I have some channel n, the quantum capacity of that channel, together with a 50% erasure channel, is at least as big as half the private capacity of that channel used alone. Okay? And just as a reminder, the 50% erasure channel acts on state rho as well. With 50% probability, it gives you rho, and with 50% probability, it gives you some erasure flag. Okay, now let's think about why this implies this superactivation effect that I claim. Okay, so the quantum capacity of this, well, let's let n be one of these channels that has positive private capacity, but zero quantum capacity. Okay? Then the quantum capacity of this channel is zero. That's what I told you by hypothesis. The quantum capacity of this 50% erasure channel is zero because symmetric channels have zero quantum capacity. However, this lower bound for the joint capacity is strictly positive because of, again, what I told you about this positive partial transpose channel having positive private capacity. Okay? So as an immediate corollary, we get these pair of channels that has zero individual capacities but positive joint capacities. Okay, I think I will skip the proof ideas, okay, and go right to the interpretation of this result. Well, first of all, this is completely different from what happens classically, okay? And it depends crucially on selecting entangled code words between the two uses of the channels. All right, and somehow these two different channels have very complementary capacities, or very complementary strengths. And the capabilities of the two different channels combine in a synergistic way that allows them to sort of cancel out, one of them cancel out the weakness of the other. So for example, one of them is symmetric, so it can't have any quantum capacity because of the no cloning principle. And the other one, it's PPT, which means it's rather noisy. On the other hand, it has private classical capacity, which somehow gives it a certain strength. And it turns out that you can take this symmetric channel and activate that private capacity and turn it into a quantum capacity if you use it correctly. Okay, and this leads us, I guess, to an interesting question. If these channels are transmitting different sorts of quantum information, what are these different kinds of quantum information, and can we characterize them? And that's something I don't know. Okay, so here are some more technical implications. First of all, it turns out that the quantum capacity is not convex. What does that mean? Well, I already told you about these two channels, and if you have one of them or if you have the other, it's, neither one is good to you, but you can use the two together. It turns out, in fact, if some adversary tells you, sort of flips some coins and selects which to give you, and doesn't tell you which channel to give you, gives you channel 1 with probability P and channel 2 with probability 1 minus P, still, that channel, the mixture of these two zero quantum capacity channels has a positive capacity of its own. All right? So you don't even need to know which channel it is you got. You just have to have some probability of having both channels, and you have positive joint capacity. And another consequence of what I've been telling you is that this coherent information quantity is actually a poor approximation to the quantum capacity, which means choosing quantum error correcting codes randomly, in fact, is strictly suboptimal. So this coherent information characterizes how well random codes work for your channel. Okay? And it turns out you can have channels where if you just looked at how random codes behave, you would guess that the capacity is 0. But in fact, when you look at the overall capacity by choosing more clever error correction procedures, you can have some large fraction of the maximum possible capacity for that channel. Okay, these are just some other comments I want to make of work that's been going on. First of all, this privacy seemed to be very important in getting the non-additivity. That theorem I showed you basically told you that if you have private capacity, you can somehow activate that privacy and get quantum capacity. But it turns out you can do something very similar for channels that have no private capacity either. So somehow private capacity isn't the magic thing isn't the magic answer to what kind of information does this channel transmit. And it turns out that even this private capacity, which characterizes the capability of the channel for doing quantum cryptography, is very non-additive too. So you get this effect where two channels, neither of which is very good for quantum cryptography, you put them together, you get very good channel. Okay? And in fact, you don't need to do this in the asymptotic setting. So there are, now what do I mean by that? You remember this quantum capacity was defined in terms of many uses of the channel. And we're talking all the time about what's the rate at which you can transmit information in the limit of many channel uses. Okay? But it turns out you can actually find channels with fixed dimension that have this property. If I give you, there's channel 1, channel 2. If I give you many, many copies of channel 1, it's no good. You can't transmit any quantum information. Similarly for channel 2. But if I give you one copy of channel 1 and one copy of channel 2, you put them together, you can transmit quantum information. Okay, so here's a summary of the talk. First of all, quantum information theory, it sort of gives us the ultimate limits on communication and cryptography as well as information transmission. Quantum information is very different from classical, so it can't be copied and it's very delicate, and as a result, the theory of quantum error correction is really important in the theory of quantum information. The quantum capacity gives us a sort of holy grail for error correction. It tells us the best rate at which we could hope to do error correction, and can also guide our design for more practical error correction techniques. And it turns out that very noisy quantum channels can interact in fairly surprising ways, and in fact, the surprises are good. It means that these things that look very useless, that look useless to us, too noisy to transmit any information, can actually combine in a synergistic way and be useful when we use them together. Okay, here's a long list of things, of interesting topics, I think, in the theory of quantum information that I haven't managed to cover. There's a whole theory of multiple user channels, so many senders and a single receiver, many receivers and a single sender, understanding the theory of quantum networks, but you should really be careful if you were going to think about this in the quantum setting, because even in the classical setting, some of these multi-user problems are hard. Of course, these quantum capacities, they tell us the optimal rates at which we can transmit quantum information, but they don't tell us practical ways to achieve them. So it would be nice to find practical ways to, sort of practical constructions for error correcting codes that come close to these optimal bounds that we get. Okay? There's a whole story of quantum error correction and fault tolerance on trying to do operations on your encoded data, and that's actually very interesting too. I think I'll just leave this here, and if you want to read it a bit, fine. Otherwise, we'll ask questions. Thanks.
You said you can't use the mutual information in quantum case to define the channel. But is there any meaningful? So I think you can still define the mutual information for a quantum system, right?
Yes.
Because you can define the conditional probabilities. So is there a physical, meaningful interpretation for mutual information in this context, or is it useless? I mean,
No, actually, it's very useful. So I can just draw a picture. So in the classical setting, right, the mutual information is just, it tells you the capacity. In the quantum setting, if I have some channel that maps some A system to some B system, and then I say, not only do I have the channel, but I allow the sender and receiver as much entanglement as they like. Okay, so they can start with a lot of entangled pairs. Right? Those things are no good for transmitting information themselves, right? Because, well, you know, look, no signaling, right? Given an entangled state, it's not possible to use transmit information. So you can imagine, what if I gave these guys as much free entanglement as they want? How much quantum information can I transmit with this channel? And the answer turns out to be just the mutual information. Oh, so what I do is I take some quantum state, rho A prime A, and I hold on to the A prime system, and I act on the A system with the channel. Okay. Then the mutual information between A prime and B just tells me the quantum capacity is the capacity. Yeah. Sorry, does that make sense? Oh, in fact, yeah, yes, that's right. But this is now quantum mutual information, right? So it's the entropy of A prime, the von Neumann, plus the entropy of B minus the joint.